So in this video, we want to take a quick look at the graphs of exponential function and the logarithmic function. We don't want to spend a ton of time on this. We just kind of want to see the graphs so that we're kind of familiar with the general shape of them. So in particular, I think it's good to look at e to the x and the natural log of x. E is just a really special number when it comes to these exponential equations. It comes up by far the most common, the most often of them. So let's just go ahead and take a look at the graph. But it's important to note that no matter what the base is of the exponential function, as long as it's not 1 or 0 or something weird like that, they're all going to have the same general shape. Okay. So we'll just pick some points here and we'll see what this would be. Okay. So first of all, if we pick 0, we're always going to get 1. And that's not special with e, that's going to be for any base, right? If we pick 1, we're going to get e in this case, which is about 2.718. If we pick 2, we're going to get e squared. I think it's like 6 point something, approximately. If we go the other way now, meaning if we pick like -1, we're going to get 1 over e. So this is 1 over 2.718. So a little bit less than a half, right? Between a half and a third. Put in -2, we're going to get 1 over e squared. Okay. So e squared is actually 7.389. So it's a little off there. But anyway, so it's between 1/7 and 1/8. Well, we don't need the exact values. What I want to try to look at is what would happen. Like, let's just say we put in like -100. Okay. And we can write that down actually, -100. So this is going to be 1 over e to the 100th. Okay. Now, e to the 100th is a very large number, very large. So 1 over e to the 100th is very, very small in terms of getting closer to 0, not negative, but getting closer to 0. Okay. Now, if we just keep decreasing the numbers here, say we put in -1,000,000, we're going to get 1 over e to the 1,000,000. So that's going to be so close to 0. But it's never actually going to touch 0. So let's just plot some of these points on the graph and kind of get a feel for what it would look like here. So we have a point at 1, 0, 1 rather, 0, 1. We have a point at 1, e. So if this is 2, this is 3. Point's going to be about right here, right? Let's say 4, 5, 6, 7, 8. So 2, e squared would be about right there. So -1, -2, -3. So at -1, we have 1 over e. So again, between 1/2 and 1/3. So like right there. -2, it's getting even closer. So as we go closer this way, it's going to get closer and closer to that x-axis, right? Closer and closer to 0. And then it's going to kind of explode as we go this way. Okay. So it grows extremely slowly until we reach a certain point where it just starts to explode. Okay. And, this is what it means for something to have exponential growth. Okay. And we'll switch over to the graphing calculator in a second here, so we can see a better picture of these graphs. Let's write down the logarithmic graph first, though. Okay. So f of x equals natural log of x now. Oh, and by the way, on the exponential graph, the getting closer and closer to 0, we call that an asymptote. Okay. And we usually represent it with a dotted line. Okay. So we have a dotted line at y equals 0, and we call that an asymptote. Okay, we'll look at this a little bit more when we talk about limits. This is what we would, like the way we would talk about this when we talk about limits is that the limit as x goes to negative infinity of f of x equals 0. Okay. So I think it's better to just kind of talk about it in that context. A lot of times in algebra, you just kind of like tiptoe around that, and then you get to limits and you're like, oh, it's just a limit. So I think it's better just to save it for when we actually talk about what limits are and all that. But yeah, so this does have a name though, which is asymptote. And we saw this on the rational function graphs as well. Or rational functions can have both vertical and horizontal asymptotes. Okay. I think we looked at those graphs anyway. I'm trying to remember. I think that we looked at those on the graphing calculator on Desmos, if I'm not mistaken. So now with the natural log, I'll do the points over here this time, I guess. Let's look at those same points, which will run into issues, of course, because namely with the negatives, we can't plug in those negatives, right? So let's just forget that, I guess. And in fact, 0, we can't plug in 0 either. We can't plug in 1. 1 is going to be 0, right? In fact, we know these are inverse graphs of each other, so we could just flip these points around, right? When we know that if we plug in e, we're going to get out 1. If we plug in e squared, we're going to get out 2. If we plug in 1 over e, we're going to get out negative 1. If we plug in 1 over e squared, we're going to get out negative 2. Okay. So let's do that. Okay, if we plug in 1, we're going to get out 0. E, we're going to get out 1. E squared, we'll get out 2. 1 over e, negative 1. 1 over e squared, negative 2. Okay. So just to picture this shape based on the e to the x graph, we know that inverse functions, we can reflect the graph over the line y equals x, and that will give us the inverse function graph. So this is what the logarithm graph is going to look like. Okay, it's going to be this graph reflected over that purple dotted line there. So we're going to have a point at 1, 0, e 1, which will be about right here. Okay, e squared. So we have 1, 2, 3, 4, 5, 6, 7, 8. Okay, so like right here. Okay. And then 1 over e, negative 1. So like right here, 1 over e squared, negative 2. So like right here. And now, again, we can't plug in 0. So we can't see what's happening at x equals 0, but we can keep plugging in numbers closer to 0. And we'll see that it's just going to keep getting smaller and smaller. If we plug in, as we see here, 1 over e to the 100th, we're going to get out negative 100. If we plug in 1 over e to the 1 millionth, we're going to get negative a million. So it's going to keep going down to the negative, towards negative infinity. And it's going to keep, we can keep getting closer and closer to the line x equals 0, but we're never going to touch it. So we again have an asymptote right there, a vertical asymptote this time. Okay, so this one, let me draw that a bit better here. Yeah, that wasn't that much better. That's okay. So this one we have a vertical asymptote, which corresponds to our domain issue, which is not a coincidence. Okay. And believe it or not, the even though the logarithmic graph, it gets really flat, it looks like it's getting really flat, it actually will go out to infinity as x goes to infinity. So it'll keep growing forever. It just does it very, very slowly. So yeah, so let's go ahead and look at these on a better graph, on a graphing calculator. Okay, so I'm gonna put in e to the x here, and then natural log of x here, and zoom out here. So the red line here is e to the x, the blue line is natural log of x. So if we zoom out, you can see what we're talking about with the horizontal asymptote here. Okay. So the graphing calculator, you can see that as the x's get smaller and smaller, f of x is getting closer and closer to 0, e to the x in particular. Now on the graphing calculator, it actually looks like it touches 0, but they're just rounding. You can see even at negative 7.35, it's already at 0.001. So they keep going and they're just rounding. So it just says 0, but it's actually just really close to 0. It's not actually 0. Okay. Same thing with the logarithm graph. Okay. You can see as we get closer to 0, the numbers are getting smaller and smaller, but we can never touch 0 over there. Okay. Again, the exponential graph blows up, gets really big, really fast. The logarithm graph, it really doesn't. It's pretty flat looking. It does not get very large very quickly, but it still will grow infinitely. We can still say that as x goes to infinity, f of x does go to infinity. Even though it really looks like it's going to converge at a number, it doesn't. It just goes up super slowly. Okay. And then you can see that these are reflections of each other, of course. So even the asymptote gets reflected from the line y equals 0 to the line x equals 0. So yeah. So this is hopefully a clearer picture of those graphs, and we can see it cross those 1 here, 1, 0, and 0, 1 over here.